working as a faculty in the Department of Naval Architecture and Offshore Engineering. So today we are going to see about laws of thermodynamics. So thermodynamics has its applications in various systems where heat transfer plays a vital role. And laws of thermodynamics, almost every system where heat transfer plays a vital role is governed by the laws of thermodynamics. Or I can say laws of thermodynamics provides the fundamental base for the functioning of all systems where heat transfer plays a vital role. In today's session, we are going to see about all laws of thermodynamics. So first, I would like to begin with zeroth law of thermodynamics. I have three systems A, B and C. System A is in thermal equilibrium with system B, which means system A and system B are at same temperature. And system C again is in thermal equilibrium with system B. So which means system B and system C are at same temperature. That is, they are in thermal equilibrium. But there is no direct contact between system A and system C. If this is the condition that exists, then I can say A and C will be at same temperature, or A and C will be in thermal equilibrium among themselves. So zeroth law, it states when two bodies are in thermal equilibrium with a third body, even though there are no interconnections in between them, so two bodies are in thermal equilibrium separately with a third body, then I can say they are in thermal equilibrium among themselves. Say I have three classrooms A, B and C, this room, the next room and next room. This room and next room are at same temperature, and this room, the next room, the room present to my left hand side are at same temperature, but the middle room is the contact point for the room present on left hand side as well as the room present on right hand side. There is no direct contact between the room present to my right hand side and the room present to my left hand side, but it means if this condition exists, that is my room and the room present on left hand side are at same temperature, and my room and the room present to my right hand side are at same temperature, then I can say even though there are no direct contact between the room present to my right hand side and to my left hand side, I can say they are also at same temperature, and all these rooms exist in thermal equilibrium among themselves. Meaning is all these three systems exist, or all these three systems are at same temperature. So thermal equilibrium means all these three bodies are at same temperature. So this is about zeroth law of thermodynamics. Next, first law of thermodynamics is based upon law of conservation of energy. So energy can neither be created nor be destroyed. Actually, first law, it states when a closed system undergoes a cyclic process, net heat transfer will be equal to net work transfer. And mathematically, it is given as heat transfer Q is equal to work done W plus dU, change in internal energy. Q is equal to W plus dU. Q stands for heat transfer, W stands for work transfer, dU stands for change in internal energy. Before that, what is internal energy? Internal energy is any object is made up of atoms and molecules. Any substance or any object is made up of atoms and molecules. In a particular substance, there will be a movement of atoms and molecules. The energy possessed by any particular object or any particular substance due to the movement of molecules is internal energy. When temperature increases, internal energy will increase. I can say change in internal energy is directly proportional to change in temperature. Example, you would have seen when you heat water. When you heat water, you can see water droplets which is present at the bottom of the vessel travel up to the top in the form of bubbles. What it indicates is when you increase the temperature, energy increases. That is, when temperature is increased, internal energy is increased. But practically, first law of thermodynamics is not fully correct. Meaning is, when I supply 100 kilojoule of heat to an engine, all 100 kilojoules cannot be converted into equal amount of work done. There will be some losses. Say for example, in an engine, let it be in an automobile engine, a bike engine or a car engine, what happens is coolant carries some amount of heat and exhaust gas moving out of the silencer carries some amount of heat. Frictional losses are there. So practically speaking, we cannot convert all the heat put into equal amount of work done. There will be some losses. This is the first limitation of first law of thermodynamics. Next, coming to the second limitation. Say for example, I have this pointer which is present at 50 degree and my body will be at 28 degree or 30 degree, so which is this room temperature. So obviously energy will flow from 50 degree Celsius pointer to 30 degree Celsius me, that is my body, till thermal equilibrium is established between my body and the remote. So by nature, energy flows from high temperature to low temperature. But this first law did not give any info regarding the direction of flow of heat. So whether heat flows from high temperature body to low temperature body or low temperature body to high temperature body. In this heat transfer process, I can say the high temperature body which supplies heat is source and the low temperature body which receives heat is sink. Normally energy will flow from source high temperature body to sink, which is low temperature body. But this first law did not convey any info regarding the direction of flow of heat, whether heat flows from source to sink or heat flows from sink to source. So these are all the limitations of first law. I said earlier there is no restriction on the direction of flow of heat. So these are all the limitations of first law of thermodynamics. Applications of first law of thermodynamics involves a few processes. So what are all the processes? Constant volume process or isochoric process, constant pressure process or isobaric process where pressure is constant, or isothermal process or constant temperature process, and hyperbolic process, and isentropic process, and polytropic process. These are all a few examples of applications of first law of thermodynamics to closed systems. Now we'll get into second law of thermodynamics. Second law of thermodynamics has two statements. So number one, it is Kelvin-Planck statement. Number two, it is Clausius statement. First, I would like to go with Kelvin-Planck statement. So I can say Kelvin-Planck statement, it is the fundamental statement or it is the statement by which all internal combustion engines present in this world work. So Kelvin-Planck statement, it states it is impossible to construct an engine. You cannot construct an engine which when working in a cyclic process, it works in a cyclic process, which can convert all the heat from a single thermal reservoir into equal amount of work done. Practically speaking, losses will be there. Example, you can take your bike. What happens is the exhaust gas moving out of the silencer carries some amount of heat, and if it is an air-cooled engine, air carries some amount of heat. If it is a liquid-cooled engine like R15, again liquid coolant carries some amount of heat, and frictional losses are there, radiative losses. So second law of thermodynamics is practically correct. So next we'll get into the second statement, that is Clausius statement. We would have seen by nature energy flows from high temperature to low temperature. I was quoting an example that energy should get transferred from 50 degrees Celsius remote to 30 degrees Celsius my body. So basically energy gets transferred from high temperature body to low temperature body. But take an air conditioned room. The room is at 17 degree, but the outer ambience is at 35 degree or 36 degree. Of course, since we are in southern India, right now the outer ambience will be at 38 degree. See, room is at 17 degree, but the outer ambience is at, probably I can say, it is at 37 degree. So energy gets transferred from 17 degree Celsius room to 37 degree Celsius outer ambience, which is against nature. So Clausius statement states it is impossible to transfer heat from a low temperature body to a high temperature body without any external work. That is, by nature energy flows from high temperature to low temperature. But if you want to make the energy to flow from low temperature to high temperature, you have to provide some work as input. See, in the engine you are getting work as output due to which your vehicle is moving. But in case of a fridge or AC, you are providing work as an input, and which component provides that work input is compressor. You provide electric power to your compressor, motor. The motor converts electrical to mechanical energy, and that mechanical energy is used to operate your compressor. So you provide external work as input to a refrigeration system or for an air conditioning system. In turn, you get cooling effect as an output. So basically, it is impossible for you to transfer heat from a low temperature body to high temperature body without any external work. So this is about second law of thermodynamics, Kelvin-Planck statement and Clausius statement. Next, we'll get into third law of thermodynamics. So third law of thermodynamics, it states the entropy of a closed system at thermodynamic equilibrium approaches a constant value when its temperature approaches absolute zero. That is, you can say the entropy of a closed system. You are going to consider the entropy of a closed system, and that system need to exist in thermodynamic equilibrium, which approaches a constant value when its temperature approaches absolute zero. So the entropy of closed system approaches a constant value when that particular system is at thermodynamic equilibrium, when the temperature generally approaches absolute zero. See, here meaning is you have a system which exists in thermodynamic equilibrium by satisfying the three different equilibrium conditions: mechanical, chemical, as well as your thermal equilibrium. And what is that particular system approaches a constant value when temperature approaches absolute zero. So this is about third law of thermodynamics. Thank you.